that's been, yes, the meeting's being recorded. So conventionally, the training data is defined by visual assessment and on-screen delineation of high spatial resolution satellite data. So an example of that, this whole talk, it's about, the example is around burnt area mapping. I'm with the MODIS fire team, have been for 20 more years now. So this is an early collection 1 MODIS 500-meter burnt area product. This is an animation. So we take a time series of MODIS data, and at the pixel level, we, using a kind of somewhat of a physics-based algorithm, can detect the day of burning, which is the color and the location at 500 meters. We make a monthly product, but this is just an animation over a 5-month period. In Botswana, that big green hand is the Okavango Delta, which is the largest inland water delta in the world. So it took us about 20 years to validate that product to what's called stage 3, which is under statistical sampling. And the way we did that is we got 558 Landsat 8 2-date image pairs. So that's Landsat 8 images 16 days apart. The square blobs show you those images. And then we did we interpreted at 30 meter, which is the Landsat resolution, if burning occurred between the 2 dates. So here's an example. This is Okavango Delta again in Botswana. So this is a Landsat image, 185 by 185 kilometers. This is about a month later, and the yellow vectors is what's burnt between the 2 periods. So very time consuming to generate that kind of data set. This is cloud free. We'd also have an unmapped class, but then you would compare the yellow vector with the MODIS product in that same time period, and then you could calculate a confusion matrix. But equally speaking, you could use the yellow vector as training data for classification if you were developing a classifier. As I said, it's a bottleneck. And the real issue now, the emphasis for my research interest really in all of this was, we are now making, and the community is making, products with Sentinel-2 and Landsat, which are medium resolution. They're about 30 meters. So the idea of collecting training data with minimum error at higher resolution than the thing that you're trying to classify or validate is quite problematic, because we validated MODIS 500-meter data with Landsat 30-meter data. So if we're making Sentinel Landsat 30-meter products, how are we going to validate them? And how are we going to do that when we're looking at pre and post change? That's actually becomes really difficult. Google Earth, for example, doesn't have high-res data with a really temporary rich archive. So here's an example. This is a 30-meter burnt area product made with what's called NASA harmonized Landsat Sentinel-2. This is just 1 month of burning. Top right is just, if you know Sentinel, you know it's 110 by 110 degree tiles. It's just a small subset. Just zooming in. So this is all the way across Africa. This is a single month, 30 meter. The colors in show the day of burning in that month. And this is the MODIS products at 500 meters, which is nice. They're kind of coherent. And you can see, as we'd expect, far more small burns mapped at 30 meter than at 500 meter. If you're into atmospheric emissions, or if you're into land management, this is incredibly important. But how do we validate it? And so how are we going to validate these data? And so in an early paper, what we decided to do is use PlanetScope data. And so this is this is a very small area, 1.8 kilometer by 3.6 kilometer, 30 meter burn area, and this is PlanetScope data. And so at that point, we didn't have much PlanetScope data, but it works. You know, the PlanetScope data is 3 meter pixels. It's really small. What you're seeing there is savanna tree canopies. You're also seeing the burn. And so under NASA CSDA funding, we managed to acquire a large amount of PlanetScope data. This paper got published last week. This is a global analysis of the availability of PlanetScope high resolution data. And so we looked at 12 months of metadata, about 176 million images. The PlanetScope is a constellation currently of 3 sensor generations. There are typically 100 to 133 sensors on orbit per month. So they provide, you see in this big image here on the right, this is the analysis showing the average revisit. It's in the sinusoidal projection. But the take-home message is we have about a 30-hour global median average revisit, which is incredible. That's like data every 30 hours globally red, green, blue, near infrared surface reflectance. So phenomenal. So we can now start using these data for classification, training data, also for validation. So we got NASA funding a year or so ago, well, a year ago, just started, where we're going to develop training data from PlanetScope time series using deep learning. Vitor is my co-author on this, is the more of a deep learning expert than I am. And at the end of the day, we're going to develop some new techniques to do that. We're going to use an active learning approach, which I don't have time to talk about. And we're going to provide the data to the public. So, you know, this project is very germane to this subject. So here's just some recent examples. What we did is we used the MODIS burnt area data that I showed earlier in the talk, the 558 locations, which took about 3 or 4 years to collect, which is Landsat based at 30 meter, 2 dates. And we used that with a transfer learning experiment to classify a bunch of PlanetScope 30 meter pairs, so pre and post pairs, to see if we can actually do burnt area mapping. We weren't sure if this was going to work. We just did it as a way of, you know, testing our software flows. So here's an example. This is somewhere in Madagascar. This is 1 day. This is 1 day later. We got loads of these. I just show this one because there's no clouds in it, so it's easier to understand. So you can see the burns, right? And then this was just an early version. So we basically, this is the UNet deep learning classification. But the thing is, we train the classifier with the Landsat data set, not PlanetScope data. Landsat has completely different bands to PlanetScope, but it still kind of works. One of the things that's interesting when you think about doing this conventionally, you know, in the past, I would use things like random forests where we use per pixel classification, collect training data at the pixel level. When you do deep learning, conventionally, you use something like a 256 by 256 patch. So when you want to start thinking about how you can do the classification and the validation, you need to make sure they don't overlap. So this is just a kind of illustration. These are 2 images of Landsat. They look a bit funny because of the way we derive the data, but the big blobby thing in the middle, the white blobby horse-looking shape, is a burn. And for every burn derived at 30 meters in the training data for the Landsat training data, we just cast a window around the centroid. And then we did that kind of a random process. This enables the gray squares, which are used for training, and the gray squares are the validation, the red squares are the training. Then they're independent, which is a desirable property. In this way, we get a hell of a lot of data, and we do this across, you know, lots of scenes. This is currently in preparation. Vitor's writing this up. The map on the right just shows the location of the PlanetScope pairs. There's multiple pairs through time. On the left are just some examples from left to right: Zambia, Ethiopia, Lesotho, Madagascar. And on the bottom is the classification result, where green means there's very good agreement between the classification and the training data, which was derived independently. In this case, to do the validation of the PlanetScope, we had to do it again. We had to do that manually. But we got less than 10% omission and commission error, which is awesome. Really quite surprising. So penultimate slide. Training data derivation is challenging when you think about change product generation and validation. And so this is just kind of saying, well, PlanetScope seems to be like a good approach because we now have the temporal revisit you need, and we got it at the resolution, which is much higher, 3 to 4 meters, compared to, say, Sentinel 10, 20, or 60 meter, or Landsat at 30 meter, which is desirable. And as I've just showed you, potentially machine learning can be applied to help derive the higher spatial resolution training data, which is the objective of the Access project. What I just showed you was a transfer learning experiment, which was not really under the Access project. So therefore, reusability of training data is already a reality for certain machine learning applications. We use 30-meter Landsat training data derived for MODIS product validation application to develop a unit to classify 3-meter. So we did it already. We didn't expect it to work so well, but it did, which is good. And obviously, and I've been at other meetings today, but I'm sure that was discussed today, you know, things like ARD, analysis ready data, so the NASA harmonized Landsat Sentinel dataset or the USGS Landsat ARD, and things like open access repositories like the Radiant Hub stuff that people are now working with. We're trying to collaborate with them. which provide repositories for training data and machine learning models. There's new opportunities, right? But clearly the community requires development of interoperable machine learning training data, so standardized machine readable data and metadata formats for easy application of training data that they're needed. And maybe Stack, which is a metadata kind of thing, is a good way of doing it. We think it probably is. Penultimate slide is when we did this work with PlanetScope, and we're using it with time series. In this example, it's just date 1, date 2. This is PlanetScope. It's about 20 kilometers by 10 kilometers roughly. You know, when you've got time series in your training data, you've really got to work out how you're going to like get that into this standardized format. So that's actually quite unique. It's not like doing a static land cover classification. And the other point here is that certain commercial satellite data, such as PlanetScope, they're not always freely open. That company sells the data. They just announced today that they're going to make all the data available to anyone that's got National Science Foundation funding, as well as NASA. But you know, you can't actually provide all the input data because there will be users who won't be able to access it, or they have to go and buy it. So the kind of needed metadata, you know, just off the back of a beer mat, off the top of our heads, the kind of things that would need to be included in training data for machine learning, which is patch-based deep learning, would be an input list, the list of the parent image files. So in this case, date 1 TIFF, date 2 TIFF. The patch dimensions, they're not always 256 by 256. Some kind of scheme like patch numbering, 1, 2, 3, for example, in this example. The coordinates, usually in remote sensing, we usually look at the northwest or the top left corner. And so you need to define that in each parent image, because the images aren't going to be aligned. PlanetScope are not aligned, they're different orbits, and some kind of legend. And then on top of that, you then actually have to have the data format, whether it's a GeoTIFF, a COG, or whatever you want to use. I think that's more straightforward. So I wanted to provide that as food for thought. This project, because we aim to provide clean, quality controlled label training data to the public at the end of this 3-year project, we're very interested and keen to continue this dialogue to make our data interoperable and try and help develop the interoperability of the machine learning training data, however that's going to happen. And yeah, I think, you know, the only thing that I think we're bringing that's new to the table that you guys don't already know is this idea of, you know, the challenges of doing that in time. And I'll finish there. Thank you.
Great, thanks, David. So any questions for David? I see Chris has chimed in. What about spectral bands? Do we need to standardize representation of that at the data level?
Yeah, that's an amazingly difficult question to answer. Thanks for that, Chris. Because if you take, for example, PlanetScope, there's 3 generations of sensors. The spectral response functions are different between the generations. Indeed, the bands are different on some of them. So you could make the argument you don't need to if you've got the file names, because you're basically saying, here's my classification, my training data raster, and then here are all the inputs that we use to make it, right? This basically, that metadata kind of thing I just showed, means it's very efficient, right? There's not a lot of information, you know. Ideally, in the more simple case, your training data is the data, you know, Landsat chip, and the output, you know, the training classification. But when you're doing it through time, that starts to be a lot of data, even with a small chip. So yeah, you know, that's a good question. I didn't really answer it because I need to think about it. I think the metadata thing I just showed you means you don't need to do that. But I can imagine some users going, why the hell do I have to go and obtain all this PlanetScope data? Why can't you just give me it? And so, yeah. And then there are some issues with, you know, the geolocation through time of these input data sets as well, and the processing level. And with this conversation could be broadened. Because I wanted to do this quickly, I didn't list everything. So yeah, that was something we'd have to think about.
So one thing I was just curious about, you mentioned the PlanetScope data. Is that reshareable? You know, so you get access to it as a NASA investigator, and then you do this classification or validation. Can you then share that classified data?
No.
Okay.
That was easy.
Yeah, I was afraid of that.
What we can share is the derived products. Okay. And in the paper that we just got published, that some of the reviewers pushed back on that. They accused us of advertising a commercial company, which really we weren't. And we have a co-author on that paper who's from PlanetScope, Rasmus Hoberg, who's their chief remote sensing kind of guy and a developer. And they have an education program, so any individual on the planet who's affiliated with an education establishment can get free PlanetScope data, but it's limited. It's not like thousands of images.
Right.
And then there are data buys. The Norwegian government, for example, have bought global coverages of PlanetScope data, which are freely available to anyone recently, to support tropical forest monitoring. So, yeah, I mean, I think, I think it's those constraints are there, but if we develop training data with like I don't know 10,000 images. If it was really useful, I'm sure that could be negotiated as well with Planet. They seem to be pretty open to that.
Okay. So one last question from Douglas. He notes on change detection applications, the time when change occurs could affect the model performance depending on the data used. So for the training data, what will be the best way to document that to make it usable for future applications?
Oh, yeah, I apologize. So when Vitor made this draft of the slide, he actually had the file names for the 2 PlanetScope images. I mean, they were faked for this presentation. So the any decent satellite provider, so even the European Space Agency does this, that's my joke, provides the sensor date acquisition time in the file name, right? That's nearly always the case. Landsat does that. Most of the MODIS standard products do that. Sentinel products do that. And if they don't, other people will have it in their metadata, in which case it does start to be a problem. So that's a good question. But in general, I think there's an understanding that satellite product producers have file names that follow the convention of sensor acquisition date time. MODIS stuff would also do the collection version and the processing time as well, and then some kind of coordinate location or tile scheme if it's Landsat. So that is a good question. That's something that would need to be thought through for those people that don't have good file names on their products.
Okay, thank you. I think we need to move on, but that was really good, David. Thank you. So Gabby, you're up next.
Great. Hello. Can you see my screen?
We can. Yes, thank you.
Excellent. Can you still see my screen?
We still can.
Excellent. Hi, my name is Gabby, and I'm a machine learning engineer with NASA Harvest. I'll be talking about our experience with these ML-ready remote sensing datasets. I'm going to start by briefly elaborating on my background. So I come first from a software engineering machine learning background, and I've been working with Harvest on applying machine learning to remote sensing data over the last year and a bit. So I've worked on implementing and deploying machine learning algorithms in a range of domains, from marketing to drought forecasting to agriculture to solar energy. So kind of to emphasize that I think my background and the perspective I'm coming from is maybe a little bit different than a lot of other folks here. So I'm going to talk today about how we can develop machine learning ready data sets for remote sensing. What does it mean to have a machine learning ready data set? In my mind, such a data set achieves 3 main goals. First, it reduces barriers to entry to interacting with the data. So it's easy for machine learning practitioners to interact with the data set. Secondly, it allows different groups to compare algorithmic advances on the data set. And finally, it makes it easy to extend models trained on the data and apply them to real world use cases. So to ground this a little, I'm going to use an example from computer vision. This code downloads ImageNet, which is a data set of 14 million labeled images, into a PyTorch dataset object. And PyTorch is a common machine learning framework. This object then gets passed to a data loader, which handles a lot of machine learning, like nuances such as multiprocessing, shuffling, batching the data, etc. So this approach achieves 2 of the 3 main goals I described before. First, it makes it super easy for ML people to get started with the data set. And it makes it easy for different groups to compare algorithmic advances against the data set. And I'll describe how. So firstly, what's being handled for us? The downloading of the data set is completely handled in that code. I don't need to worry about where it's being hosted or what format it's in. The ImageNet class handles it for me and gets me back data that can immediately be passed into a machine learning model. And second, there's an easy integration into machine learning frameworks. In this case, I automatically get a PyTorch dataset object, which is commonly used to handle data in PyTorch. So I don't need to learn, as a machine learning person, any new abstractions to handle this data. Finally, the train test split is universal. So that means that anyone who trains on this dataset can compare their results and be confident in their comparisons. The catch here is that this ImageNet object is extremely opinionated on what the dataset will be used for. So it's specifically intended to be used to classify images according to the classes defined by ImageNet in 2012. If you wanted to use this dataset for other things, such as bounding box detection or image segmentation, then you're out of luck. So as a comparison, I'm going to talk about what it felt like when I started interacting with Earth observation data, and I'll focus on some of the challenges I came across. The biggest challenge is that unlike in images where the labels, unlike in images, in Earth observation data, the labels and observations are highly decoupled. So whereas for ImageNet, I can be confident that all of the models were trained on the same image label pairs, this is much harder to guarantee in Earth observation. Specifically, there are lots of choices you can make in Earth observation, which makes it super difficult to compare results from different machine learning algorithms on similar tasks. A few which have stood out to me are the choice of satellite imagery, the spatial and temporal resolution of the data, any processing which was conducted on the dataset, for instance, cloud removal. And these choices can have a significant effect on the ultimate performance of the model, sometimes more than the model choice itself. And that's just for the model inputs. Labels are often collected in projects with specific goals in mind, which means lots of data exploration is required before they can be integrated into any pipeline. As a visual example, here is a labeled dataset in Rwanda, where the label locations are highlighted in red. They're extremely dense because they were originally collected for drone imagery, not satellite imagery. Naively dropping this into a pipeline for instance, Sentinel-2 satellite imagery is likely to lead to overlapping labels because of the coarser resolution of the satellite data. So this heterogeneity makes it hard to take anything for granted when working with geospatial data. Some exploration is always necessary. Projects such as Stack significantly help reduce the overhead when dealing with new datasets, but some ramp up remains necessary to be able to plug this dataset into a machine learning model, just because of the natural variation I described before, not to mention needing to learn a new API, the Stack API. So I've kind of presented two extremes of how data can be presented. On the one hand, you have Torch Vision's data loaders, which really strictly define how the data should be used. And there are benefits to this. So there's an ease of algorithm comparison. By having a standardized train test split, the users need very little time to understand how to use the data, but this also introduces limitations on how the data can be used. On the other hand, many geospatial data sets today are quite close to raw data, and this gives users lots of flexibility on how they should be used, but it also means that a lot of time needs to be dedicated to processing the data. So at Harvest, we're working on creating a dataset and an accompanying pip installable Python module, which acts somewhere in between. By having strong opinions about how the data should be used, it allows non-Earth observation folks to easily explore the data. However, we've tried hard to keep the data as flexible as possible so that it can be applied to other use cases too. So the main goals of CropHarvest are to take many different Earth observation datasets, specifically related to agriculture, and combine them into something which can easily be shared. It's to lower the barriers to entry for machine learning practitioners who want to start using Earth observation data, and it's to create shared methods for comparing algorithm for crop type classification from remote sensing data. To create this dataset, we aggregated a number of datasets yielding over 90,000 labels in total with global coverage. All labels have a crop or non-crop attribute, and 31,000 have more granular like crop land use attributes as well, covering 356 different classes. So all these labels are combined into a single GeoJSON file. This allows anyone with a text editor to begin exploring the entire dataset. In addition, we defined a standard description for each dataset, in this case by fixing the columns across all of the datasets. This means it's relatively easy to understand, as you only need to understand 12 columns. One challenge here is that different datasets are collected by different projects with different goals in mind, and this makes them heterogeneous and difficult to combine. As an example, here are two different labels collected by two different data collectors. It'd be difficult to homogenize the data without losing the more granular information, in this case, replacing the more granular groundnut label with the coarser groundnut and peanut label. An additional challenge is that this data set is extremely imbalanced with a long tail of classes with very few examples. So on this graph, the y-axis is the number of samples in a class, and the x-axis is the specific class. To homogenize the labels without losing information and to better handle the long tail distribution, we supplemented the row labels with higher level classifications using the FAO's indicative crop classification classes. So returning to the previous example, the peanuts and peanuts or groundnuts labels remain distinct to keep the most granular level of information, but they're now assigned the same higher level class, in this case, oilseeds. In addition, we included remote sensing data from 4 data sources as input to construct a 12 time step pixel time series for each pixel, where each time step represents 30 days. So we took Sentinel-2 L1C, and we took the least cloudy pixel in the 30-day window. For Sentinel-1, we took the median of pixels within the 30 days, or the closest one, if none was available. For ERA 5 climatology, we took precipitation and 2-meter temperature. And finally, we took SRTM topography data, which remains static throughout the time series, but we can also get the slope from this. An additional challenge we noticed when speaking to other machine learning folks working in agriculture and remote sensing was a lack of standardized data sets with which we could compare algorithms. As an example, we were discussing with a different team whether a meta-learning based approach we were developing might work for their problem. We were both working on crop type classification, but had collected unique data sets, both of which contained proprietary data. The only way we could compare models was for us to eventually get permission to contribute to their codebase and then rebuild our model so that it would work within what they'd built. This introduced a lot of friction for the relatively simple task of comparing different approaches to crop type classification. One way we tried to handle this is in the CropHarvest dataset by introducing 4 test tasks, covering a range of in-distribution dataset sizes and agroecologies. As I mentioned before, an important goal was to lower the barriers of accessibility to start using this data. So here's some code to load the test tasks I just described. The second cell creates all the tasks. In addition, it automatically downloads the data, so you don't need to think about where it's hosted, which is Zenodo, or the format it's hosted in, which is GeoJSON and TIFF-tiles. These datasets are equivalent to PyTorch dataset objects, meaning they can just be dropped into a data loader and a training loop. And there's an additional asArray function, which returns NumPy arrays, so they can easily be integrated into scikit-learn workflows as well, which is what you see here to train a random forest classifier against the data. And finally, we implement a range of evaluations within the CropHarvest package, meaning it's straightforward to take some predictions and evaluate the performance of the models. Yeah, so to conclude, Earth observation data is hard and harder than some other subdomains of machine learning. But at Harvest, we're trying to mitigate some of this difficulty by defining a specific task for which Earth observation data can be applied, crop type classification, and designing a toolkit which makes it easier for machine learning practitioners to dive in. And of course, there are still challenges from a machine learning perspective, but hopefully this project will lower the challenges from a data management perspective. Yep, thanks for listening.
Great, thanks, Gabby. We have one question already. If anybody else has questions, please put them in the chat. This one comes from Douglas. Assuming there are multiple versions of a data set, which there often are in earth science, how does the data downloading / loading procedure document or record those versions to ensure the reproducibility?
Yeah, that's a good question. The way that we're planning on handling this is to basically version the code with the data. So if you download the pip package at a certain version, then you're getting a certain version of the data as well. Yeah.
So would that affect how then it might be reused in another context? I mean, well, yes, obviously, but never mind, just sort of thinking out loud. Again, from Douglas, the CropHarvest looks great for ML practitioners who use Python ecosystem. How feasible can it be used to another language, R, Julia, et cetera?
Yeah, so right now it's only in Python because that's the language that we use at NASA Harvest, but the core functionality shouldn't be difficult to port over to a different language. So if there's interest, that's definitely something we'd be interested in speaking to you about.
Great. Any other, oh, here one's from David. UMD, University of Maryland, I think, agricultural crop mapping usually done using tens to hundreds of temporal metrics, percentiles of bands and base ND ratios. Does this create a challenge?
Yeah, so over the last few months, we've tried to migrate to using close to like raw data, so not using pre-computed features and focusing on methods which allow us to successfully do this. So as you were doing in your talk, we're also looking at deep learning methods. So I guess we haven't encountered the challenge yet.
Okay. All right, well, thank you. We will now turn to our final speaker. Chris, are you ready to go?
Sure, yes, let me try to share my screen. It usually goes wrong, but I hope today is going to be a good day. Okay, that looks good. Now I just need to bring up the presentation. Yeah, perfect. Okay, sorry. Close your eyes.
Yep, we're good.
Just trying to go to the beginning. Okay, hi everybody. I'm very honored to have been invited to give a talk on RainBench towards data-driven global precipitation forecasting from satellite imagery. So this is work that has been presented, for example, at AAAI, and I'm going to focus on the data engineering aspects today. And at this point, also a shout out to my co-author, Catherine Tong, and all the others who have been involved in this work. Just a quick motivation of how this project came about. So there are going to be more frequent extreme precipitation events, most likely, as climate change progresses. That sort of has a huge impact on particularly farmers in the developing world. So if they get a one-day forecast, they don't have enough time to harvest, for example. But if they get like a 5-day forecast, weather forecast, then they can probably harvest most of their crops. So the importance of having these sort of medium-term weather forecasts, even in areas, for example, in West Africa, where the current forecast quality is not very good, is very important. One problem that we have is that numerical forecasting is predicted to soon hit a power limit. So if we want to improve our forecasting quality, we need to go to higher data resolution. It is forecasted even by 2025, actually the computers who are going to make these numerical forecasts might create electricity bills that cannot be paid even by like large institutions anymore. That's quite interesting. At the same time, we have some other much cruder methods for weather prediction, for example, persistence, where we assume that things are just going to go on as they did in the last hour, or climatology, where we're essentially looking at like how has the same day been over the past 10 years. If we compose this all together, you can see this here on the right-hand lower side. Then you see that there's this window for like forecast days of forecast lengths of a few days, where numerical weather prediction is like by far the best performer. So as a way out of this problem of having to get better forecasts, there's this idea of directly predicting the weather from data. And by data, I mean satellite data, I mean reanalysis data, whatever data is available. What we have provided in our work is both like a benchmark suite for machine learning for global data-driven weather forecasting, because when we have lead times of a few days, then we actually need to input pretty much the whole globe as a context. While for now casting, maybe just the US might be enough, for the US at least. And then also we introduce a new data pipeline for these kinds of problems called PyRain. And actually, the need for a new data pipeline arose for some subtle reasons that I want to dive into now. First of all, maybe a quick overview of what kind of data we're dealing with. So like we packaged data that was previously available from different sources. So for example, we have some simulated satellite data. So simulated satellite data doesn't have these partial observability issues that you have like with real satellite data. So it's like a good starting point for method development. And then we have iMerge, which has a really good precipitation estimation product, reanalysis data by NASA. And then we have ERA 5, which is a very good reanalysis product by the ECMWF. So the subtle problems that we ran into were mostly arising from the fact that in order to feed our training samples into the neural network, actually what we need to do is we need to compose a lot of different slices across a lot of different variables in these geospatial data sets, where like each slice is of course like a two-dimensional slice. So it could be like variables like temperature or precipitation at a given time, but then also I want to provide like context from several time steps. The way that the data is usually supplied is in netcdf files. Usually have like one file for like 1 day. Across like, I don't know, 10 years or however much context you need. And the sort of traditional way of dealing with so many files would be like to just put Dask on top of this. And we did that, and we figured that it's extremely slow, of course, to provide for this random access that you need during a network training, right? So you need to access these patterns in like a random fashion. Yeah, so then we looked into like how people actually solving this problem, and we figured out, okay, so there's one camp that actually just rewrites each of these samples explicitly, puts that in a bucket, for example, using TF records, yeah, then just trains from that bucket. So for us, the problem was we didn't really know what our sample composition would be, because you know, we needed to figure this out during research. And then also we figured, okay, so if you have relatively small data sets, even if they're like 1 terabyte in total, like you can, and then like, you know, you need to take like 50 slices for each sample, and you write this out, then you have a factor 50 larger data set in the bucket. So like you move from 1 terabyte to 50 terabytes. But if you go to even higher resolutions, and let's say my data set is like 10 terabytes already, then I have to write 500 terabytes into a bucket. And if I have to rewrite this because I want to have a different sample structure, for example, that can get quite bad actually. And also, of course, in the bucket, we don't have sequential access, which can also be bad for research purposes. On the other hand, some other people were just rewriting everything into a HDF data set. And here, you can't write it into a bucket. You need to keep it on an SSD, but SSDs also tend to have a limited maximum volume. So that might also not scale. So we were thinking about how can we prevent the rewriting of this data so we can experiment quickly with a lot of different samples, and also not use up so much processing power on our cluster while we were trying to keep our GPUs from starving. So like each GPU to die, like, you know, depending on what kind of model you train, what kind of GPU you have, but like it consumes about like 0.5 gigabyte to actually 1 or even 2 gigabytes of data a second. Then you're reading from your SSD, particularly like you have not only like a ceiling on the total bandwidth of data you can read per second, but also the number of operations. So what we came up with was actually using a structure that is very old, and it's called memmaps. And memmaps have this amazing feature that the operating system like directly maps physical address space into virtual address space, and that saves you about a factor 10 of kernel interrupts that you would have like any other method that is based on file access, so including HDF and everything else. What we noticed, and then also it has this great inbuilt feature called paging, which is essentially then basically prefetching data from disk into memory automatically. What we figured out was that that actually is by far the fastest yeah, also resource process that also uses like least processing resources on the cluster, and saturates your data bandwidth in terms of reading from SSD. Like you can keep your data, you don't have to rewrite, you can just keep it on, for example, local SSDs. You can have multiple local SSDs to increase the total throughput. Yeah, you get all of this for free. One issue with this approach is, of course, that like you need to be a little bit careful about the access ordering of your data. So like the random read performance can vary depending on like what your major or minor access is. Obviously, like you then need to handle lots of this sort of metadata stuff manually, because unlike HDF and so far, there's not really a support by like a major data handling framework for memmaps directly, unfortunately, at this point, as far as we could find. So then we actually figured out we need to do this bookkeeping. We need to provide this bookkeeping. So it's just a very quick comparison with like the original NetCDF approach. You can see that NetCDF and DAS definitely not solution. So we said, okay, we need to provide all this bookkeeping as well, because otherwise people cannot use memmaps. And I think this is also the main reason why people don't tend to use memmaps. So we came up with like a declarative style towards like constructing these samples. So you just define, essentially you configure how your samples are going to look like. So here you just partition your set, and then you can essentially just write down, okay, I want to have these and these slices, time slices from these and these variables at this and this resolution, and so on. I can even like interleave like different sample structures. So I can desample from different sample modes, and I can interpolate and so on. And then like I have this special data set that I can construct, and that's just entirely compatible with the whole PyTorch infrastructure. You can just put this in a data loader, and then everything is taken care of. So for example, with memmaps, like there are some things you need to keep in mind when you do multiprocessing and so on. And our framework does this all automatically. And then as well, like we provide all the data as memmaps actually. So the data is not compressible anyway. So that's also a difference. If you have highly compressible data sets, you might do better with like SAR or something like this, because then the bottleneck is not like the reading from disk, but then it's better to read the compressed data from disk and uncompress it in RAM than obviously reading like the uncompressed data from disk. What can you do with this stuff? Well, I'm just going through this really quickly. I mean, we also provide some benchmark tasks, and actually it's quite hard to beat climatology. Because you have also sequential access still with your member data sets. Like you can also do a lot of analysis very easily, which is very nice for like research purposes. There's a lot of stuff in terms of method development that needs to be done, and I would invite everybody to take part in this. There's a lot of opportunity. Remember, we have this power limit problem with numerical forecast, so it's important to solve this. And so this whole work should also be seen in this like context of creating a digital twin of the Earth eventually. And we hope that just going back to the roots and really using the amazing hardware that we have. So I remember I started computing in like 2000 whatever, and if I think of what possibilities we have now, it's incredible, like the bandwidth we have and so on, and the memory that we have. But if you don't use this efficiently, we're losing some of that gain. So Pyron is sort of like going back to roots and saying like, what is the most efficient way of handling this? So Pyron is available open source, RainBench is also available for download, and release expected. No, it has been released by now. I should have changed that. Thanks a lot for listening, and thanks to everybody who has been involved in the project, has been helping with. Thank you. Any questions?
Thank you, Chris. That was a lot to take in.
I'm sorry.
Douglas,
I'm really sorry.
I think Douglas has a raised hand. So, or someone, Douglas, I think.
Okay. Go ahead, Douglas. I didn't know you could.
I have a quick question for you, Chris. More about the process instead of the technology part, because I noticed this project is it's developed under the Frontier Development Lab Challenge.
Yes.
So could you describe how that process came along? Because the challenge or hackathon style things has been really popular in developing different like training and benchmark data sets to be able to use for other machine learning applications.
Yeah, so for everybody who doesn't know about the Frontier Development Lab, it's this amazing public-private partnership between companies like NVIDIA or NASA in the US and University of Oxford and ESA in Europe and other partners, of course. And it takes place every year in the summer. It's like a 2-month, it's just like a 2-month stretch, and you form different task forces. So my task force included about 7 people, and our task was to make some progress towards extreme weather prediction over like sort of medium term. Yeah, you start off with like a boot camp for a week, and then you sort of spent another 2 weeks or so to define your different goals that you could have during the project, and you start implementing these projects, and yet you have like a research showcase. You also have a research showcase in the middle of the project, and yeah, it's like it's very stressful, but it's super exciting, and like you get to work with all these amazing people. You even get paid for that work. And the spirit is to release as much as possible into the public domain. So as we've done with RainBench, and there's even like the spaceml.org, I think it's called. They even have like their own benchmark data set, hosting platform, where you can also find RainBench. And usually our projects also lead to publications. So we tend to publish at New York's workshops at the very least, but like once in a while, like we also get like full conference papers out of this, depending on like how we can best sell this, and obviously like this invitation to ESEP, this is also indicative of yeah, how we are all like yeah, related to the whole geospatial like data engineering community. Yeah, does that answer your question? Sorry, I've been talking for a long time now, but I'm not sure if I've said what you.
Yep.
Were really interested in.
Yeah, thanks. I really like to talk with you more like later on how we can organize something similar like this.
Definitely. Yeah, sure. Thank you.
Yeah, I think a lot of ESIP members would be interested in something like that.
Okay.
Any other questions for Chris? Okay, so the exercise now is where we're really going to start to try and answer the central question of the session is, what does machine learning data interoperability actually mean? So you're going to you'll be automatically distributed into 5 different breakout groups, and we'll go through an exercise that each group will have a leader to tell you what you're doing. But basically just sort of exploring what themes we might be able to identify and things that we could address as a working group and as a cluster going forward. So Annie, I think you can let us go just maybe. So also everybody, there's within the Kiko chat window, you'll see a link to the notes document where I hope actually you put your name as a participant. But then also there's a link to the notes document for the different breakout groups. So it's just breakout group 1, 2, 3, 4, 5. So if you could name our groups 1, 2, 3, 4, 5, Annie, that'd be great.
Yep, they are named 1 through 5. And just a reminder, as you go into breakout rooms, that this isn't a, you can still be a fly in the wall and an active listener. So just wanting to put that out there. And to the co-conveners of the session, hold on for just a minute. After I'll send you into everyone will get sent into rooms, but then I'm going to assign you all to a specific room. So I will do that right now.
Okay, wait just a second.
Oh, yep.
Conveners, you're going to have 1 minute when you come back. We'll come back for 5 minutes, and you'll have 1 minute or maybe like 45 seconds to just give your key takeaway message that came out of your working group. Then the working group will work through the details at our next meeting, but just share that one sort of takeaway when you come back.
Okay. Right. Welcome back, everyone. Hopefully you weren't too abruptly yanked back in from productive conversation, though I imagine you were.
You yanked back a little early, Annie, but that's okay.
Oh, I was thinking you needed 15. Do you want to go?
I was only thinking 5, but
Oh,
I think it's all right. I mean, group leads, how did you do? We got most of the way through 3 questions. I mean, it might be valuable to just sort of see if any common themes have emerged across the groups. I mean, it's hard to have a group discussion of 38, but that's a much smaller number than the 65 we had when we started. Yeah, I think trying to reorient and go back into groups again would we spend too much time logisticizing. So, well, I can tell you this sort of theme that came out of our group was that really this is a common goal of data stewardship writ large, is that you want to make your data as usable, as shareable across as many communities as possible. And we're not really entirely sure that there is anything unique about or special about training data interoperability. We also had a little bit of debate on whether reuse is the right term, because you're always doing sort of a different application for the training data. But the idea that if you can, by well documenting your data, by presenting in a consistent format, by using common terminologies, which are all good things to do regardless, you're going to lower the effort that's needed to make that data a good training data set. I think that was our basic takeaway. Does anybody want to add anything to that?
I actually agree with you. I think that also came out of our breakout, that really all the principles that you would apply to any other data set to be interoperable, it kind of goes in the same direction. It's only that we may not have developed the techniques or standards or conventions that cover training, machine learning training data sets particularly. But that's
Well,
more of that kind of work.
And maybe that's the gap, is what are those conventions that are necessary. Nothing in our 15 minutes, nothing really leapt out as, except for maybe consistency of labels was something that came up.
Yes, correct.
Using common
exactly.
terminology for labels, like the one that Gabby talked about, peanuts.
Tyler raised her hand.
Go
I
ahead,
just saw it. So
yeah, so an interesting thing that came out in our group was we didn't have an answer for it, but a potential something that we really need to think about balancing is do we prepare data specifically for machine learning and for a particular machine learning framework in particular that would make it, if you specifically convert the data into a format that is more usable within a particular machine learning framework, then it makes it much easier to use for people who use that framework, right? But then the contrarian view was that sort of breaks interoperability, because if you're not using that particular framework, then this customized data set is actually less useful for you. So it's a difficult question of how specific do you want to get to make it more usable for a very specific user community, or do you use something that's more general, which would, it sort of makes it less usable for the people who you would customize it for. But I don't know, it was an interesting balance.
Well, but I wonder, and maybe this isn't really the problem of the person who's doing the original machine learning exercise, and it's more of a problem of a data steward that might preserve the training data set, but it should be available in multiple formats so that it could work in multiple frameworks. I mean, that's the sort of rule of thumb for generic interoperability. Data are available ideally in several formats if possible, but
Yeah,
when we're talking terabytes, that's not always possible.
Yeah, that's kind of consensus from our group as well, to make it to a wider audience for applications. And we also talk about the need for community standards for the training data, for the better training data interoperabilities, particularly for time series, whether it's single pixel or patches.
Oh, okay. So there's actually something specific in terms of like those conventions that Alexander was mentioning that is particular to machine learning. You know, time is always something, but in capturing it by the pixel of the patch, that's sort of a unique feature. Is that
right? I think most of the aspect you mentioned about they're applicable for any other data as well, but for training data particularly, there's something unique just for training purpose, then that needs to be captured.
Right.
Christian raised their hand.
Yeah, I saw that. I was just going to say, go ahead, Kristen.
Oh, yeah, I just wanted to elaborate on this quickly. So it's actually about access patterns of the data, and those are very different between machine learning applications and like traditional users. So if I have netcdf files, they're really nice to load into Panoply and do some climate analysis with it. But like if I need to do random access and I've got my data distributed in like 1,000 different files, it's going to be extremely slow. So that's one thing. So because doing model training, particularly deep learning, like you need to sample your samples IID. So like you need to be randomized, and at every epoch that order needs to be re-randomized. I think that's the major difference. And then there's like spatial subsampling or temporal subsampling is also something that needs to be addressed within that. So there certainly are different clusters in terms of who needs to access the data and what pattern. And I think this is what we need to think about.
Yeah, so do you think one could begin to define maybe a set of access patterns? I like that term.
I actually think that might be a good direction. And then there are a lot of different existing solutions for like all these different access patterns, and also some competing ones. And then like, you know, you need to think of like, how do I store this data ultimately with all the nice metadata and whatever? And then how can I, you know, convert it and provide it for download, like, or like, you know, let the user convert it in place, or you know, provide it as download already in some format, or how do I do this best? And I think there's really something to be done. Yeah.
So basically, what I think you're going towards is that interoperable really assumes the aspect of data access and to some degree performance that goes interoperability. So, you know, not only metadata, not only describing labels and having uniform labels, but actually organizing the data that prefers or supports data access that is efficient for the machine learning application. And that it is in a way done that actually that in the storage system that is going to be used, optimized for that storage system. So let's not be specific to cloud, although we all think about cloud now as the given. All right, we have a question in the chat. I think I just saw it.
Yeah, Christian, there's Joe from HDF, appropriately, is asking, when you say CDF access is slow, do you have a benchmark to compare it against?
Yeah, so I just gave a talk. Actually, we did a comparison that we put Dask on top of the netcdf files that we get from downloading ERA 5, which are usually like, you know, 1 file per day or maybe 1 file per month even. And we compared that against like the fastest possible as we could think of, which is just rewriting everything in a single mem maps. And actually the performance is like, I think we were 50 times faster for mem maps. And it was actually tangible because we were starving our GPUs. And then HDF like is also pretty fast, but not quite as fast as mem map, just before you ask, but I don't have the precise comparison.
I just saw a question from Ken. Every big data user want the data to be efficiently accessible. Are AI ML application really any different in this regard? I would say there are differences in how frequent the machine learning applications require efficient access, because we in the model, like Christian just mentioned, when you do a deep neural net, it needs really frequent access to those like big data, and so that can creates multiply effect on how that may slow down the process. And in some traditional applications, you just access data once, and then you can do your model. Some of that linear or like physical based model that will be like less intensive, like frequent access to that.
Yeah, and Chris comments on the randomness of the access is a new wrinkle. I agree with that. That was sort of an insight I got. And Seth, I think the guidance on storage patterns that will give you efficiency for MLUs sounds like it would be valuable. And so I think that sort of corresponds to this access patterns. Given a set of access patterns, what sort of storage is going to be is optimal for those different access patterns? And is it possible to really meet more than one, or is how does that work? Yeah, I think that requires greater exploration.
I think one comment I want to bring up is when we're talking about interoperability and the reuse, that we need to have all those data available at some point in somewhere. So, and in our group, we have discussed maybe, that's my idea, for the founders, require all the researchers to share their machine learning training data that use to develop their machine learning models in, for example, in the founders at data center, in a way to make it discoverable. And that's the first step to make it interoperable, because if you do not have the training data out there, nobody can really access that or reuse that unless they send you an email, ask for that data.
Right. No, I think that's key. And this is one of the things that NASA is concerned about, is they want a strategy for how to make these data available. And is it just, something additional to the DACs that handle NASA data, or is it something special, which is what I think we're trying to probe? And Ken, I don't think you're being contrary, you're just being realistic.
Well, and this, what you just said about NASA is directly true about NOAA as well. I mean, we are gearing up heavily to try to make our data more machine learning, AI ready, more cloud optimized. All of these things are hugely important, and we need these answers now. I guess at a certain level, though, maybe I am being contrarian, because maybe it's not so much the details of the conversation, but I'm kind of hearing a lot of things I've heard over the years about, oh, my community is special. And I don't know, I feel like I can quickly come up with examples, randomness of access. As I mentioned, I was computing singular value decompositions back in my postdoc day, and I had to randomly shuffle the data around and randomly access it. I don't know, I don't feel like that's necessarily anything new. I'm really intense. I'm not trying to derail the conversation, but I want to make sure whatever we do, it's useful for as many people as possible.
That, I think, is the bottom line. That's probably a nice takeaway message, and that's sort of what came out of our breakout. And Tyler, Douglas, unfortunately, I wasn't able to attend your session, but it seems like that was a similar theme that came out of your session a couple of days ago, right? That this isn't necessarily new. It's just the problem continues, and this is yet another new big data use, but it's not necessarily changing the problem in fundamental ways.
Well, no, so actually it is new in a way, and it's new because of cloud. So in the old days, you downloaded the data to your own machine and you organized it however you wanted for your problem. Nowadays, what we're trying to do, because the data are so big, is we're trying to set up the data in a way that at least most of the users that are accessing big data don't have to actually move the data and can actually access them in place where they are. In order for that to work, those data have to be in some kind of a structure and an orientation that doesn't make that an anti-pattern, that doesn't completely slow down the big data things you want to do. So that's the new part, I think, is that confluence of cloud data, access in place with these different access methods. We do want to try to match some of those, at least, if not all of them.
I agree with that. I wonder how much machine learning is done at the data. I think it's still done old school way, even if it is using cloud storage.
Yeah, I think that brings to another topic, is the cost of moving things to the cloud. So if you do not access the data in a way that's efficient, then the cost of you doing a machine learning or the deep learning model on the cloud would just be unimaginable when you do things inefficiently. So that's one reason that scare people don't to do things on the cloud.
Yeah, but I think the idea there is that the training data is much smaller in volume and dimensionality than the data that you're classifying. So you take the training data to the cloud potentially, or because it's so light, it's in the cloud already. And then at that point, moving data into the cloud, that's a perennial problem anyway, outside of this conversation. if you know what I mean.
Chris, why don't you give us the last word?
Oh dear. Okay. Yeah. No. I just wanted to get back to this idea of like these problems are new and these problems are not new. And I think like part of the problem is also like there's a huge ecosystem that's being built for data handling for machine learning. And I have the feeling sometimes these solutions are geared towards very specific use cases, but the machine learning community maybe could learn how to do things more efficiently. So I think like a set of guidelines of like, you know, what are the common access patterns and like what are the existing solutions and how should we go about these things? I think there's also a lot that actually can be taught to machine learning researchers here, right?
Yeah,
and maybe that's the final word.
No, that was a nice summary. Okay, we're at the end of the session. Thank you all. This was really helpful. If you're interested, there is an AI data readiness cluster in ESIP. We encourage you to join. And although the Earth Science Data Systems Working Groups is sort of a NASA thing, outsiders are certainly welcome. And there is a close association between the ESDSWG and ESIP. In fact, ESIP often hosts the ESDSWG meetings. So we'd love to keep you involved, stay in touch. Thank you for the link, Tyler, and I will capture all the chat in the notes as well. Thanks all. Take care.
Thanks, everyone.
Thanks.
Thanks,
folks.